Okay with that? Okay. So while we are there, I would like to have some sort of feedback. Of course, we just made an hour, so you have seen that this is pretty hands-on course, and we will try to work together and to do some things together if we are enough. For the moment, my target was between 5 and 10 persons, so I don't mind if there is less people than the lecture before. So you now you get the way that we are doing this mini course. So basically, we will exploit the possibility of Pandas because Pandas is rather an immediately using software, so it's very usable, like people from software say. I mean, you will not be an expert of Kalfa techniques with 10 hours with me, but you will have some ideas of how to go on. Today, we would like to work on where we can get the databases. Um, this is quite important because um, especially if you are using commercial software or someone else is using, you believe that everything is you get the software, someone else provides the databases, and then you are done. You have everything you need. No, this is not the case. We will see that's already difficult to put together binary databases. We will see that it is possible to get them for free, basically from the Japanese Society of Material Science, which is called NIMS, NIMS, and from there you can get some databases. I have sent you in email in the zipped file. You have three open databases: one for iron, one for aluminum, and one for copper. The aluminum one is from a project of the European community and is quite good. Also, the iron-based materials are adapted from um, other sources which are partly free and partly commercial from a software which is made in Austria, and its name is Matkauk. And finally, there is this copper open multi-component database that I have developed some years ago, which is still in its infancy. So where we can get and do the game. So I will switch. Please, we are 1, 2, 3, 4, 5, something like 9 persons. So if you would like to switch on your microphone, I don't think it is a trouble. If you want to make comments, answers, or what else. So I will do. Are you now? You see my window on Pandat? Hope yes or no?
Not
No.
yet.
So
No, not yet. Now? Yes? No?
Yes.
Yes, okay.
Okay. Yet. So I am using an older version, but basically it is the same. Um, what I want to show you, because I can do this in real time, let us create a new workspace. Let us, this is the full version. Let us upload a certain open database and see what we can do. I would like to open this, we can do this one. High entropy database that I have not created by myself. But, and then when we can select components, 1, 2, 3, 4, 5 components, and once we are done there, we do all the binary phase diagram based on iron, for instance, and this is the way that it works. You can do practically the same things with your own version of Pandas, but as long as you are limited to 3 components, it is not possible to run five um, five phase diagrams at once, like we are running for this case. But you can have the patience to do them two by two, up to you, or to open a database which no, to open a workspace that has been already worked out. So now I want you uh, file create. You open your Pandat, please, all of you, if you are attending, of course, and then you have the second zip file. You have it somewhere, and so you should open a workspace. Open workspace, and you will open these CU binaries. No. CU binaries Miani CU 2018 one. Can you do that? This one? Yes, no, perhaps. I don't. The right answer should be I cannot find a file. Let me go into this window. Is there someone who's able to have this picture on your own Pandat?
I think I am able to have it.
Yeah, okay, good, thank you. So once you have it, this is done by myself, but you could have done the same work loading the single 2 components database, and then you will open all the databases, sorry, all the graphs, not the database, all the graphs you need for that. What I want you to do, or what we can do together. So these graphs, these binary phase diagrams, have been obtained by using a single, quite big, multi-component database that I've been creating, which is not totally satisfying, but it is open, and there is no other possible opportunity to exploit better open data. Of course, it is possible to have much better commercial data. Now, I want you to try to understand what it is good and what it is wrong on that, because there are some things which are good enough and some things that which are not so good. So, can you open your browser and go to the NIMS, so this Japanese people site, and have a window like the one I will show you. I will show you there. Now you should look at my screen, not a specific application. Are you? You have my screen on your screen or no?
Yes.
Yeah.
Yes.
Okay. So normally I find it with that Teams NIMS Calfad, but you have the link also on the files that I've sent you, and you should arrive something like there, because you need to make the registration if you have not already done it in order to log in. Can you do this registration if you have not done it yet? Yes, no, I have no.
Yes, I did
Or
it.
what? Lorenzo, you have already done it?
Yeah, I did it this morning.
Okay. Um, anyone that, so if you have done it, it's okay. If you need time to do it, please ask me now, because we are just a few, some 10 persons, so we have the time to do this. So what I want you to do now, register. Once you have registered, you log in. I am already logged in. And then you will find a periodic table of the elements, and you will find quite a lot of databases which are open. Um, as I mentioned, there is a specific DOI for this one if you will ever use it in the future. And this is a, a quite big collection of data taken from many scientific papers, which is open. What do we need? We need them for copper. And for copper, we can download single binary databases. Let us go. I don't remember if it is good. I know for some elements are really not good. For someone are not too bad. Let us try to download this one file, which is for aluminum and copper. We will save in the directory we need. Possibly, I would suggest that you don't save it as a text file, but directly like a thermodynamic database. So all the files, if you have not an Italian PC, and you will cat.txt extension, and we will just leave a TDB extension. But if you are not able to do it, you can still rename the file afterwards. Okay. Yeah, okay, I'm good. Now, in your Pandat, you should upload this database that you have downloaded. Need to find it. Let me check where I have missed where I put it in. Okay. So just a second. Yeah. You select the only two components, and you make your phase diagram. You can use this section calculation as far as I hope you remember this icon there. But please keep copper on the left. So you will use 0 there, 100 there, 0 there, 100 there, and 100 here, and 0 there in this window. Then you will copy data like we did last time, last lecture, and you will paste them. you see there are quite big differences after all in this one. So you see that even you can try to manage different multi-component databases. I was thinking that this one was good actually. And you can have very, very different pictures and phases and so on. I think we should now try to do together the same game, trying to assess which are good, which are not. This is not satisfying at all. And to download these thermodynamic databases, you should organize yourself because I need to have a feedback. I don't know how good you are. Maybe you are very good and you don't need to do anything. And maybe you need to, like Stefano, you need to teach me what you are doing. But sometimes it's good to get some information. Of course, we have limited time and I don't want you to lose too much time, but I need to have a feedback. Do you want to do it by your own? Someone that wants to do real time, we have plenty of time to check if we can do or what.
Could we perhaps do one more? I think
Yeah,
I
please.
missed a
Please, Zach.
couple of
Yeah,
steps.
please, Zach.
So
So
one more
now,
would be.
okay. So now you are now. So this game could be done with all the three uh, databases and workspaces. So Zach, now you have opened a workspace and then you download an open database and you are comparing them. Okay, this is the game we are doing. So let
Yes.
us go in another direction. Um, these databases are extremely useful because uh, you can compare. They are for free. They've been collected over. So let us see copper, um, copper silver, which we have been working out previously. Can you follow me, Zach? So I want to speak now with you. So
Yes,
go
I'm on this
go
same page.
yeah. So you go on the TDB file there. You download it, and I wish that you are quicker than myself in then understanding where you left the file. Possibly do not leave the txt extension, otherwise you have to rename it. And so you will save wherever you know where it will be possible to use it. I am using metallurgia03, but you can use whatever you want to. And then you save the file, and you have your file there. Remember that those thermodynamic databases file are just text file. So they have a specific structure, which we cannot explore so much, but we can see so now you are done. You have downloaded the copper silver database.
Yes.
Okay, with this extension, I think it is the name of the first highest compacted. And so now let us see. Uh, we go in. Are you in the Pandat workspace? CU binaries Miani CU blah blah blah. That which is
Yes, and
open. Okay.
I see the copper silver. I
Yeah.
see.
So you have in the left window you have a graph, and we need the graph. And then
Yeah.
you click on the graph, and then you click on the binary phase diagram. Can you see now uh,
Yes, I
the
have this
window?
exact
Okay,
thing.
good, good. Now we 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 see that it's there. This was already included in the workspace. Now we generate with your own. We load the database, which we have downloaded and we find this AGCU silver copper underscore HAY, and we load it. We select the two components. Now, maybe this is the trick that made a little mess with you. When you're doing a phase diagram, normally they go into alphabetic index. So you would find silver on the left and copper on the right. But for reasons because we have already prepared the workspace, we have copper on the left and silver on the right. So we should change the coordinates of the graph, which is instead of having 100% silver here and 0% copper there, we switch to 0 and 100 there. You are there, Zach? Or no? Should I go back? Zach, are you there?
I had an error loading the TDB file. Perhaps it's couldn't reach the page. Maybe I saved with the wrong extension, but I
Yeah,
try
you have
again.
it in the TXT. So you should. There are several possibilities, but one good possibility is that I go into the chat and I upload the file. Okay, so you can have it.
I got it now. Yeah, I thought I entered it correctly, but it overrode it and put
It
TXT.
happens. It happens. We are so if someone needs it, it's in the chat window over there. You can download it. But if you don't need it, it's okay. Hmm?
Oh, okay. And sorry, after I've loaded that, how do I superimpose it again over the?
Yeah.
Uh,
Can you load it or not?
yes, I've loaded it.
Yet.
Now.
So now you should select components. I've already selected them, but you will go into the window database, select components,
Yeah, I've got that. I've selected them.
and then you select silver and copper, okay? And then you go in this small icon, section calculation.
Oh, yes. Okay.
But as I mentioned, you put 0 instead of 100 there, here, here. What are you doing in this operation? You see there is a Y origin and X. So you want, in the graph you will produce, the Y will be 2000 degrees and 0 silver and 100% copper. And then in the origin, you will have 0 Celsius degrees and 0% again silver and 100% copper. And then this X point will be again 0 Celsius and 100% silver and 0% copper. It takes some time normally to make the decision, but then it is a sort of automatic decision. And so please trust me that we are doing the right things. So we click on that and we obtain this graph.
Yes.
Are you? And then with the right mouse, you go with the right mouse, you copy data there,
Okay.
and then you paste data there. Still, you see, it's not so good because the liquidus curve is not so good, and also this phase boundary is not so good. But we can see that, for instance, the eutectic temper is not too bad. So this is the way of collecting many and sticking together in a way, in a very naive, I would say, way, data on for multi-component databases. It took me quite a lot of time because the sources were not always so good to get. I'm still believing it is not so professional, and so I wouldn't recommend to use it for any scientific or even industrial use. The ones that I have for aluminum and iron are undoubtedly better, but this was not sort of direct use, but I want to make some hands-on exercise in order that I get what you can do or not. Any comment, any idea, any trouble from all the other people there?
So far so good.
Lorenzo? You,
Yeah, so far it's so good. Thank you.
yeah, so it's good for you. So Lorenzo, I know that
Yeah,
you
yeah,
are much more interested in iron-based alloys instead of copper.
yeah.
The game is basically the same. Now we have done it with by downloading the databases from the NIM side. In the future, people like Stefano or Sunman they will make available more complex databases. So the point is that originally, but it's up to you to decide to do it or not. uh, I wanted to you to build comparisons on those databases. I will slightly change my plan. So I want now you to do something different, which is uh, let us delete everything which we have done. So we will use again one phase diagram, and we will create a new workspace, which we have done already. And so, uh, can you find in the zip MCC CEM2 um, expanded zip the file cost 507R and load it? Yes, no?
Yes, yes.
Okay.
You can find it. So this is much better than my
Yes.
own work because this is a result of European project which has been lasting for many years with I think 30 or 40 researchers all over. It is rather dated, but it is good. And this is taken from the Open CalFAD site, and it has some slight modification by Professor Bo Sunman. So again, what I want, what I can do with my own, would say commercial full software, I can generate all binary phase diagrams. You will be able to select only 3 components. Select the ones you would like. So select aluminum. When you go to select your components, you will be able to select only 3 components. Let's say aluminum, I would recommend copper and zinc, for instance, or aluminum, copper, whatever you want. I have selected them all. And now I will do again this all binary phase diagram, keeping fixed aluminum. And you are still able to see my screen or not? Let me check. Yeah, you are still able to see my screen. So this is the reproduction of all the binary phase diagram containing aluminum. And you have already this workspace because it is on the zip file I have given to you. So this is just a sort of movie that we can see or not. It's not particularly interesting. Then I will switch. To if my computer will allow to do it to the version to your own version. Okay. So I assume that you have now your Pandat version 2020, and you will open the workspace. Can you open aluminum binaries cost 507R underscore one, this file, and this one? Yes, no?
Yes.
So again, we have better data. This is in, I see that they are in atomic fraction. You see X instead of weight. And so you have, again, your. Now we will do a very stupid thing. So database, we will load this cost database. Well, let's see where it is. Yeah, it's there. So can you load this cost thermodynamic database? Yes, no? Which is the difference? From one side, you have opened a pre-compiled workspace. On the other side, you just, and the workspace may be quite a big file. We have zipped it in order for you to download, and you can open. So, which is good of Panda, that someone else can do calculations for you or with you, perhaps, or using different. So you can compare, you can reopen the workspace, and you can see which are the results that you can make your own calculation. So what I want you to do, which is a very simple exercise, to do aluminum and boron, for instance, the two ones, and to redraw the section calculation we have done. Should not be problematic, I think. And I believe your computer will be faster because we are running simultaneously one version of Pandat, the older one, and one newer version of Pandat. This is PC in the office is a portable. I told the PC is not specifically, but specifically very smart. So now, if you copy data and you paste them in the other wing, they should be just the same. So they should be the same now.
Exactly.
It is there is something which I made some mistake,
I
but
think,
normally,
oh,
yeah,
sorry, Professor Miani, I think you have to change to weight percent. I think you have the bounds as 0 to 1, because the same thing happened to me.
yeah, but it is strange because in the you're right, but this one is reported on atomic percent as well. So you are right, and I'm sorry because I had no intention to do this one. I was very sure to do everything fine, and this is not properly what I have done. So because this is in atomic percent there. And I will now, yeah, percent. Yeah, yeah.
I think you need to, yeah,
Yeah, yeah, yeah,
option.
yeah, yeah. I understand the point. One it is
Okay, okay.
percent and one is fractions. It is normal. Thank you for your. It's like it's a little bit worse than working on a blackboard. So this is x atomic percent. So if I want to do the same graph, I must use in the options the x percent in graph. Thank you, Zach. So let us hope for a better for a better result. We have generated aluminum boron there, and we will then try to see if the two graph they overlap. If not, I'm very worried. Now they overlap. Okay. So this was a very stupid example to cut time instead of downloading it from the NIMS website in Japan. But I believe you got the idea. Yes, did you get the idea? So you can have your own databases. You can download some other databases, and you can compare them. There are also a couple of things to say more that I want to show you in this lecture, which is something quite easy, but but it is important to say. So and so let us go again on our, we create a new workspace. And would you like to load the iron based? This is, uh, I'm calling it FE Miani in Italian, but I believe you should FE if you are using English. So we will open this one. And we will select the usual two components of the iron carbon phase diagram. Can you do this? Yes, no?
Yes.
Okay. So
Yes.
once we have selected them, we want to build the iron carbon phase diagram. So we go. First of all, we want to have carbon 0% and iron 100% because we want to have iron on the left side of the phase diagram. The same we will do at lower temperature. This is so the melting temperature of iron, it is 1536 or 1538, it depends which source of data you are using, but this is a little bit too much, but never mind. And so what about the composition? Well, I wouldn't go into the x-axis that much to 100% carbon, because we already know that if we are working with steels, using something more than 1% in weight, it would be too much. Let us go into the options and go to the usual weight percent values, because it's good for me that I'm an engineer. So I will use an exaggerated content of carbon, a little bit more than the composition of cementite, which is 6.7%, and we will go in such a way. So 0, 100, 0, 100, 793. And we will obtain a phase diagram. But I would ask you to save condition, and if you will so use, for instance, iron carbon underscore one or whatever, you are with me? Can you follow me? Should I stop, go back, whatever?
Yeah. You're fine.
Okay. So we have done all the things similar to the previous cases, but we have just used maximum 7% in weight of carbon there. And we have also used this say condition option, and we have chosen a name, which is this one, iron carbon the score 01. This is generating a batch file, so a sequence of commands to be done. So let us see what we are doing in such a way. What are we getting? We are getting the iron carbon phase diagram with the graphite. Okay? This is very good for interpreting structures and phase by cast iron, but it is normally not the one that we are using with tills. So we should try to do another phase diagram, like using the same data that we've been using, but we will select phases and we will exclude, yeah, diamond because it makes a mess. So we will suspend diamond and graphite, but for what concerns here, it will be just, can you do this?
Yes.
Okay. And now we will save this condition with another name, possibly iron carbon 02. Let us see what it is happening. Now, if we click on the right button of the mouse, we see that we have excluded, so we don't see any longer graphite, but we will see, this is the cementite composition in the standard iron cementite phase diagram, all the phases we know, so especially the zone here, having excluded the graphite, we will see just this value. So it is up to you to decide which is the most useful phase diagram. Of course, if you have to deal with steels, basically we will never see graphite in steels, and so you will see cementite or maybe other higher carbon iron carbides, but this we will speak about. Are you okay with that?
Yes.
Yes.
Okay. So if you would go into this Japanese name site, you will go into iron and carbon, and you possibly will be able to download this TDBL file. This is left for you as an exercise to get if you are okay with that or not. So now you have in your hands basically two safe collection of multi-component databases which are running currently on Pandat. And I think it is good. And you have also the possibility to generate those phase diagrams. This is the binaries from aluminum, but I will close it because it making mess. So going back to those diagrams, we can do also other things that we have not done yet. Last time we have been using section calculation and solidification simulation as well. Now, in just some minutes more, I would like to make line calculations. So line calculations are generated using this small icon, or, well, for the moment, using this small. So let us go with a possibly very, very simple steel with 1% carbon and 99% iron. So it's some sort of prototype of a bearing steel. And we will fix this composition here. We will select phases. We don't want to have diamond and graphite as before. And again, we can save condition because then maybe we 2 points are identical. And we want to see what's going on from 20 degrees up to the melting point. Let us say that it is a little bit less than 15, 20 degrees should be. But let us see which are the phases which are in this line calculation. So we have now a different graph. On the x-axis we have temperatures, and on the y-axis we have the fractions, not the percent like I was making for mistake before, but we have the fraction from 1 to 0 of the other phases. Using legend and possibly options. I should change the characters because these are too little. I don't know if you are able to see that. So we see there that there is cementite, FCC-A1, which is austenite, of course, BCC-A2, which is ferrite, of course, and liquid. And we see the specific situation. Can you do this game yourself now?
Yes, I did it.
Yes.
Okay. I think doing the overlapping game would be a little bit confusing because we can do, but we could compare different phases with or without. So now we have excluded graphite, and then we will include graphite there, and we will do the same thing. Okay, and so I'm just changing the font size. Otherwise, it would be not possible, especially for a remote screen, to see anything. Again, giving legend. This is a little bit more visible, and then you will see which are the phases that we can see. We have the graphite that before we were not able to see because we have been excluding that. Okay? You are okay with that? Now, while it is useful to prepare and those batch files, because once you get out from the software and you go back again, you can reuse your calculations instead of typing by hand every one. So let's run, and we have, for instance, this iron carbon 02. And then it is running the things we need. And this is, I believe, rather useful. So we see the same results that we've been producing. Another important thing that I'll open is that our database as well, I am opening with a text editor within Pandas, but you can open in any other text editor that you would like, apart some Office applications. I think Notepad the right one. So this is a list of commands which it is about the database we've been loading, the component we have been selecting, the phases we've been suspending, and the points from where we have started and from where we want to arrive. Unfortunately, it's not very well described inside the Pandat, because I think it would be fantastic to have it, because you can write your own program like I am doing, for instance, in MATLAB or other simple applications. But it's not difficult to understand it. You can write most of those components and see what's going on. Okay? You can combine a series of calculations. For instance, for this 1% theoretical steel, 1% carbon steel, we can produce a solidification simulation, like we have using, for instance, we can use this one, the Scheil non-equilibrium rule, and we can select phases, again, avoid graphite and diamond, and we can have some extra outputs, which we will find useful in the following lectures. For instance, we can add other values or combinations of values, or even, this you will find, we will use frequently this value, which is the derivative, the derivative with 2 slashes of the temperature with the solid fraction. I'm adding the sign minus because it's convenient for me. And then we can make a specific graph using on the x-axis the solid phase fraction, and on the y-axis this calculated numerical derivative. You could also do this numerical derivative by exporting your data, for instance, in Excel, in other, and then you can do the numerical derivative as well. I will also save condition 3. Okay, So we see now the solidification curve. We have been using the child rule. If everyone is okay with the child rule, it's okay. I will not even explain about it, but of course we can spend maybe next time a little bit or more than 2 words on that. But I assume that you know it. And this is, I assume that you don't know it, which is this value. Again, I want to have bigger characters, fonts on this one, but you should believe me. So we have been creating such a graph, which is something quite important for me for the applications, because I think that these very simple numerical tools, they can explain different solidification situations. Okay, so we will find, if we want open the batch file we've been generating, we will find there. So we will see a list of values that more or less we can change, we can do many other things. Okay. So for this first view composed by lecture 1 and lecture 2, we have, I hope, learned a few commands using Pandat. We have seen that we do need databases, because without databases we cannot go on. And those databases are the result of experimental work, and people in the scientific community is going to use ab initio simulations and data, and preparing. I've been recently browsing a paper by Stefano Cultarolo, and was one of the participants here. And they are trying to integrate physics, high-level physics, with this experimental data. And in the future, maybe we will have the possibility to have very complex databases that will be synthetically, so numerically be built. But currently speaking, all the databases you will find in this Japanese NIM site, they have been extracted basically from experimental work. So from optimization of existing data, and each phase diagram, people has been working several years on that. Okay, so for me, for the moment, I am okay. If you have any other possible question, please also email me. I think we will just keep the calendar like that every Monday in the afternoon. You have now at your disposition two safe iron and aluminum databases to be used in your basic calculations. We will keep to the 3 components limit, but if we want to build with our database some specific compositions, yes, we can do. We can work with the commercial software. We can build a specific composition, and then we can leave the workspace open for you to play with it. Okay. So for the moment, that's all. If there are no additional remarks, questions, and I will meet you again next Monday. Thank you for all.
Thank you very much, Professor Miani.
Thank
Bye.
you.
Thank you.
Have a
Goodbye.
nice day, all of you.
Professor Miani.
Thank you very much.
Bye.